In section 1.9, we're going to look at how to deal with limits algebraically. So in this section, we're going to learn how to plug in the value to analyze a limit. This is going to be a very easy thing we're going to do at the beginning of each problem. We're going to use different algebraic methods to find a limit. We're going to try to understand and identify indeterminate forms, and we're going to look at the squeeze theorem and use that to calculate some limits. So the first strategy, whenever we have a limit, the first thing we're going to be doing is we're going to try to plug in the value c into x, so into the function for x. And this is like replacing what would happen to the function if x were actually equal to c. And what this is going to do is that if we get a real number out, if f of c is a real number, then this is the answer to our limit, and there's nothing left to do. And this is going to happen when f of x is a continuous function at x equals c. And that's straight from the definition that a function is continuous if the limit at x equals, or x approaches c, is equal to f of c. So if that's just a real number, then that's going to be our answer. If it is not a real number, then we're going to need to employ a different strategy. And note, this is going to be most of the problems that we deal with are ones that we're not just going to have a continuous function, because those aren't very interesting and they're very easy to deal with. So let's look at an example of one where the function is continuous and one where it's not. So here we have the limit as x approaches 3 of 2x minus 1 over x plus 3. And the first thing we're going to do is we're going to plug in the value of 3 in for x in every single spot where we have an x. This is going to give us a 2 times 3 minus 1 over 3 plus 3, which is equal to 5/6. And since that's a real number, that is the answer to our limit. Let's try it again with -3. When we plug in -3, we get 2 times -3 minus 1 over -3 plus 3, and we get a -7 over 0. And this is not a real number, so there's more work to do. So even though you may know that plugging in the value is not going to give you the answer, maybe you can see that plugging in -3 in the bottom is going to give you a 0. That's a problem. We're still going to do that because whatever this form is gives us a lot of information about what the answer might be. So let's look at some more things like that. So if we plug in that number, we don't get a real number. Sometimes we can still determine what the answer is based on whatever that form is. There's a quick note here. We have to be very careful when we're dealing with things technically, and that is we can't plug in something that's not a real number into a function. So we can't plug in infinity, and we can't really plug in values that will make the function undefined, like I did in the previous page. We got a 0 in the denominator. That's not really something we can do. So there's a little bit of technicality there. We're going to get over that by just saying that we're going to have quotation marks around that. And what that really is going to tell us is that this is not really what the answer is, but with the limit, this is kind of what's going on with those numbers. And this is just going to be shorthand to kind of let us get to the answer. So here are some things that we can determine the answer without the answer being a real number at the beginning. If you plug in the value of c and you get something like infinity on the top and a finite number on the bottom, that means the top approaches infinity, the bottom approaches a finite number, then we could just say this is going to be positive or negative infinity, because infinity is such a big number compared to a finite number, it's going to dominate and it's going to go to infinity. You have to be careful of negatives. It might be negative infinity if that finite number is negative underneath. So you have to be careful of signs in all of these. If you ever have any finite number over infinity, then that is just 0. We're saying this is some finite number over the biggest finite number you can think of, and that's going to be a number very, very close to zero, and it's just going to get closer and closer to zero as we approach infinity. If we ever get any non-zero number over zero, then that's going to tell us the answer is positive, negative infinity, or does not exist. And if we have this, there's going to be another thing we have to do, and that is analyze the one-sided limits to determine which answer is correct. Is it positive infinity? Is it negative infinity? Or is it does not exist? And finally, if we have infinity times any non-zero number, then that's just also going to be positive or negative infinity depending on signs of the non-zero number. Infinity is such a big number that if you multiply it by anything, it's also going to be infinite, with the exception of zero. And it's important that we think about this non-zero number here. If it is zero, there are issues we're going to talk about on the next page. So sometimes when we plug in the value into the function, we get a form that we're going to call indeterminate. And what indeterminate means is that we are not able to determine or come up with the answer based on that form. So we have 7 indeterminate forms. Some of these we're going to see much more than others. In fact, they're kind of listed in the order that we're going to see them a lot. We're going to see infinity over infinity, 0 over 0. Those are indeterminate forms we're going to see the most of. We're also going to see some other indeterminate forms we can see are 0 times infinity, infinity minus infinity, 0 to the 0th power, 1 to the infinity power, or infinity to the 0th power. These exponential ones we're going to see less of, but are still going to pop up here and there. So before I talk about some of these forms in more detail, let's just talk about what these forms mean. So if you see any of these pop up when you plug in the value, it means that the problem really has just begun. That means that we have more work to do before we get to the answer. There are 3 kind of things that students do that are really bad mistakes for indeterminate forms. The first one is that we cannot say at all the answer is anything if we have an indeterminate form. The whole point of that form is we have no way to determine the answer based on that. So you can't say 0 over 0 is 0 in this case because anything. You have to do more work to get it out of that form in order to answer the question. The next big mistake students make is that they know that they can't answer the question with that form, so they say that we just can't answer the question. And that's definitely not true. We just have to change the function, manipulate it algebraically, do something so we don't have an indeterminate form anymore. So if you just say that we can't figure out the answer, that's basically just leaving the problem blank. We are going to be able to determine the answer for every single limit that we have in this course. Also, an indeterminate form is not the same thing as does not exist. A limit not existing is something different here, and undefined is different than all of that. And note that we're never going to have undefined as an answer for a limit. So let's talk about a couple of these indeterminate forms and try to understand why these are indeterminate. I think the easiest one to sort of look at is this 0 times infinity. And there are kind of contradicting rules going on here. So one rule that we may have is that anything times 0 is 0. So if that is true, then we take 0 times infinity should be 0. But there's another rule that we have, which is anything times infinity is infinite. And those rules are contradicting, and that means that we aren't really able to determine what it is. Note that if we have something with this form, the answer might be 0, it might be infinity, and it might be literally any number in between. We really have no way to even rule out any number. Another one that maybe is easier to understand than that as far as contradicting rules is 0 to the 0th power. And the rules that are contradicting is that we know that 0 to any power is 0. 0 squared is 0, 0 cubed is 0, so that's one rule. The other rule is anything to the 0th power is 1. Contradicting rules, so this is an indeterminate form. And we could play this game with all 7 of these rules and have similar things. Those are just the easiest maybe to understand with the rules that we're familiar with. I also want to bring your attention to the one that probably most students forget, and that is infinity minus infinity. Everything in our algebraic lives tells us that we want this to be 0. You can cancel those out, but that's just not true. And the biggest reason for that is that there are different types of infinity, and we can label them all with infinite things, but it doesn't necessarily mean that they cancel out. And this is what I warned you against in the last section, and that is infinity is weird. Weird things occur when you deal with infinity, and algebra doesn't work the same. And this is one of those things, that infinity minus infinity is not 0. It might be infinite, it might be 0, it might be some finite number. We really have no idea to determine the answer other than changing the function itself algebraically. It's important to look at all of these and know that if you ever see this form come up, we can't say what the answer is, and it means we just have to do more work to get it out of that form. And we'll show some examples of that soon. All right, so we are going to try to use a lot of algebraic methods to simplify the limit to get it out of an indeterminate form. At this point, we are plugging in the value. If we get a real number, that's our answer. If we get some determinate form, like infinity over a finite number, we can say what the answer is. Or we have an indeterminate form. And if we have an indeterminate form, we have to try to use algebra, or that's one way to do it, is use algebra techniques to simplify or rewrite the function. So here are 3 techniques we're going to use, and please know this is not an exhaustive list. It would take way too much time to write an exhaustive list because we basically have to take care of every single algebraic technique that you've ever learned, as different things could be used for different functions. There's no one right way of doing things. But here are 3 common things that we are going to use. The first is we can cancel out common factors in a fraction. And note this is often used when confronted with the indeterminate form 0 over 0. So let's see what happens. First, we're going to try to plug in the value of 2 for this limit, x minus 1 times x minus 2 over x minus 2. When we plug in 2, we get 2 minus 1, 2 minus 2, 2 minus 2, and that is 0 over 0. I'm going to put this in quotes because it's not really a real thing we can deal with. So that's an indeterminate form, so we are stuck. We have to do something to change this limit. But note that we can cancel the x minus 2's from the top and the bottom and rewrite this limit as the limit as x approaches 2 of x minus 1. And this is a brand new limit that we can do. And now let's try plugging in 2 into that function. And we get 2 minus 1, which is 1. That's a real number, and that's our answer. I want to make a quick note about something here, which is important. It is not true that x minus 1 times x minus 2 over x minus 2 is equal to x minus 1. Those things are not the same thing. They're close to the same thing, but they're not the same thing. And they are not equal at x equals 2. And that's because there is a hole in this function, in the first one. So it is not appropriate to write x minus 1 times x minus 2 over x minus 2 equals, because you cancel out the x minus 2's. However, if you attach the limit then these things are equal because the limit never actually determines what happens at that value. We only care about what happens near the value. And what happens near the value is the same for both of those functions. So what this means is that it is very important to write the limit notation when we're doing our work here. You may want to just be lazy and not write it, but it means you are incorrect when you're doing that work. All right, some other things that we can do, which we'll see some examples of in the next video. We can combine fractions using common denominators. That's going to be most useful when we have infinity minus infinity. Two fractions, maybe we can combine into one fraction, and now it's able to solve. We're going to be rationalizing the denominator. That's also used for 0 over 0 when there's a square root involved usually. And there's lots of other things that we could do. So those are the three biggest things we're going to see. Last thing in this section is the squeeze theorem. So let's state the theorem, we'll talk about what it means, and then we'll show a quick example of how to use it. So our function in question is f of x. This is the function that we care about. And we are trying to find the limit as x approaches c of f of x. That's our question. So for instance, in our example we're going to do down here, f of x is sine of x over x squared. That's our function we care about. And we care about the limit as x approaches infinity in this case. So if we can have that the function is always less than some function and always greater than some other function, b of x and a of x. So what this means graphically is near x equals c, we have some function f of x, which is always less than some function b of x, less than or equal to, and always greater than some function a of x. So it's trapped in between those two functions. So if we have that set up and we have the limit as x approaches c of the small function and the big function equals L, then we can say with certainty that the limit of the middle function is equal to L. And what we can kind of see in the picture is that the big function and the small function are squeezing together, and they force the middle function to be the same value at that point, or the limit is the same value. So another kind of example I like to show for this is something that has nothing to do with math at all. And that is a stupid example of three brothers. All right, there is me, there is my younger brother, and there is my older brother. All right, so I am always older than my younger brother. I am always younger than my older brother. So now, if my younger brother said that he was 30 years old, and my older brother said that he was 30 years old, how old am I? Well, since I have to be trapped in between them, I also have to be 30 years old. And that's what we're doing here with functions. You are squeezing some function in order for it to be trapped in between two values that have to be the same. All right, let's look at this with functions now. This sine of x over x squared. So what we need in order to do this function, note that if I plug in infinity here, I get, let's do the, this is equal to the limit as x approaches infinity of sine over the limit as x approaches infinity of x squared. We get does not exist over infinity. And that is, we don't know what that is. That's something kind of crazy there. All right, so there is something wrong going on here. We have to do more work, or we're going to do the squeeze theorem to tell us this. So what we need is we need two functions, b and a, that are always, one is always greater than our function, one's always less than our function. They need to have the same limit as x approaches infinity. In this case, the big thing we're going to do, and this is a nice trick for the squeeze theorem, is we're going to use the fact that sine is trapped in between -1 and 1. It's not a very big function. It's always trapped in between those values. So I'm going to write this little inequality here that sine of x over x squared is always less than 1 over x squared. And sine of x over x squared is always greater than -1 over x squared. So that's true just because sine is trapped in between -1 and 1. Then I'm going to take the limit of each of these parts of the inequality, and the limit that we have for these two end ones are both going to be equal to 0. And that's because we have 1 over infinity, or -1 over infinity, in both cases, which we said is going to be just equal to 0. It's 1 over a super huge number, which is a super small number. So that means that we have the right-hand side of this inequality and the left-hand side of this inequality are both 0. And the thing that we care about is trapped in between 0 and 0, which means that it is forced to be 0 itself. So that is our answer by the squeeze theorem. Look at another example in the next video of the squeeze theorem, but it's again going to look at this sine of x or cosine of x fact, because that's a nice kind of thing that we can do early on with the squeeze theorem. In the next video, we're going to look at a bunch of practice problems going over all these rules that we just talked about.